What are we doing?
I think it should be good.
Okay.
So go for it.
Okay. So here's the paper that kind of describes this library. So this was, I collaborated with Noe DeSanto, who's a fabulous PhD student at Penn, and he gave our talk at the Haskell Symposium last year. And our goal is, like, we want it to be an expressive and efficient library, right? Maybe not, it's still a Haskell library. We're not trying to be the most blazing fast interpreter ever, but if you're playing around and you want to implement your favorite new language that you just came up with very quickly, this is what we want it to be, fast enough that you can actually play with it, right? Right. So we've taken some. I'm not going to really talk a little today about the efficiency part. I'll hint at how it is, but I won't talk about it. That's in the paper if you're curious. I want to focus in on the expressiveness, right? What can we do with this, right? Because it's based on using the type system to track the scoping in the types. And you could worry that that might be restrictive. Like you have to get the Haskell type checker to like what you're doing. And so my goal today is to demonstrate that the Haskell type checker is your friend, even when you have made such rich representation as recording the scoping level in your expression type. Okay, here's a little language. We're going to implement it. Just a simple lambda calculus with unit, functions, product, sums. Here's the concrete syntax that you might make for it. We're going to create a data type to represent the syntax. But I want you to pay attention to the binding, right? Because we have functions where x is going to be bound in e. We have unit, sums, and products and sums. And so we can do case analysis of unit, no binding. For products, we're going to bind two variables. And for sum, we're going to bind x in E1 and y in E2. Right? And it's just so that you have lots of examples of binding. OK? And what do we want to do with this? This doesn't quite fit on the screen. We want to make an interpreter for it. Here's my specification of that interpreter. Right. I'm just specifying it as this big step. And just so you see, to interpret it, you have to do substitution. We're going to do substitution. Right. So for example, this is a big step substitution-based semantics, operational semantics for this language. So if you have an application, if E1 is a function, then we can take the body of the function, plug in E2 for x, evaluate to v. That's the result of our application. Right? And if we implement an interpreter that is these rules, we have to implement capture avoiding substitution. For pairs, when we pattern match pairs, we have to do the same thing, except we have two substitutions that we have to do at the same time. Right? So we have to do a multi-substitution. Right? This is for sums, it's back to single substitution, but you have to pick which one you want. Okay, how do we do it? And this is sort of, when I talk about how to do it, I want you to think about these things, right? When we, like, these are some qualities that we want of our solution, right? We want it to be right. We want to implement that language. We don't want to implement something else, right? And so that's why I'm using these very rich types to give us confidence that we implemented the right thing. It's not going to be everything we need to have all the confidence. We probably want to run some test cases too, maybe some quick check properties, but at least the types will help us and tell us, especially since we're going to use the Bruijn indices, make sure we haven't forgotten to shift somewhere. Or I am not brave enough to use the Bruijn indices without having the types guide me. But we don't want it to be too hard, right? We want, when we look at our code, it should be declarative. That's why I use Haskell, is because it makes sense to me, right? I don't want it to be cluttered with all sorts of nonsense, right? So I want some really good abstractions when I'm working with my data structure, I have a data type for lambda terms. And I want to do everything. So this is why I'm kind of doing it a first order representation. I don't want to be limited by what kinds of operations. There still will be some limitations because I have to, every function that I write over this representation, I have to prove that it's scope preserving, or at least describe how it changes the scope. So maybe there will be some limitations there, but hopefully everything that I want to do is scope preserving, and more importantly, that I can explain to Haskell why it is. And then finally, I want to be able to run it, right? But again, I don't want the efficiency to get in way with, to interfere with the other stuff, right? I want to hide any kind of optimizations I have behind abstractions so I don't have to think about them. Okay, so here's my rebound library, and this is your sort of choose your own talk. I have three parts of this talk, right? So the first part of the talk, I just want you to understand how working with well-scoped substitutions and well-scoped terms works in Haskell, right? So this is not using the library at all, but it's kind of building up what the abstractions look like and how you might work with them. Then I want to show how we can take that language we had before and use the rebound library with it, right? Show what the library provides as opposed to if you start from scratch. And then finally, I want to convince you you can do stuff with it, right? And so I have some examples of taking that language that we have and doing things like parse, scope check, pretty print, do some random testing. This is more, I'm not going to walk through this code. This is sort of say, look, you can do it. See, try to convince you that it can do, and kind of tell you a little bit about how it works. I'm telling you this now. If you want to see more at the end, ask to speed up. If you get stuck at the beginning, that's fine. You could get all this from the tutorial site too, if you want to see this code. Okay, so we're going to start with natural numbers, right? And so our key idea here is that our expression type is going to have this index that's going to say what its scope level is. How many variables, free variables, are allowed to be in that term. And I'm going to keep track of that using numbers. Those numbers have to be in the type system. So these are my numbers. They're piano numbers. I'm not really going to talk about it, but if you see some ins with a number, that's just a type that's a number. I can add them. Okay? But my variables have to stay within a bound, right? And so you may have seen this GADT before. This is a representation of a bounded number, right? So it's isomorphic to a natural number. It's got a 0 and a successor, but its type is going to tell you how big it can be. It's not going to, the type will bound it to a certain range, right? So if I have fin where this in is a z, there aren't any elements of it. There's nothing bounded by z. And, but as long as I have at least one number in the bound, then I can have a 0. And as the bound gets bigger, I get more and more numbers, right? And if I try to have a number that's not in the bound, then I'm going to get a type error. So if I say, let's take f2, but say fin in 1, wait, no, let's do this. G equals f2. This is not going to type check, right? Because f2, right, it's not the right, it needs a bigger scope. And so I'll get a type error if I try to use one of these numbers in the wrong scope. Okay, so that's what we're gonna use for variables. We can compare them for equality. I'm not gonna go into that. Now let's look at our well-scoped lambda terms, right? And this is, let's see here, try to get it as much. Okay, this is our data type, right? So these are terms. They're indexed by n, which is the scope. And where does that matter? That matters in the variable case, where we have to have an index that's bounded by the scope. That's where we use that fin, right? A lot of the other cases, they just say, I have a term in the same scope, right? When you have a pair, the components of the pair are in the same scope as the whole pair. A couple of places increase the scope, right? So when we have a lambda, I'm using this type bind one that says, create a binder that binds one variable here, which is going to increase the scope by one. I'm using this new type to kind of introduce you to the idea that maybe we're going to have a type that marks our binders, right? It doesn't matter so much today because you'll see very soon that bind one is just term of n plus one. And here for pairs where we're binding two variables, we have bind two, and that's going to be term of 2 plus n. And in fact, I think if I just go down, you will see that, right? Right. So these are just sort of wrappers for term of 1 plus n and 2 plus n. Okay. These are examples. I'm not going to go much about it. You can see that the Haskell type checker has verified that they are all closed terms. Well, these are closed. I could put a z here. They also work in any scope, right, since they're closed, right? So it type checks with 0, but it also type checks with n for any of them. Maybe it's not the best way to create it, and you can use techniques like Sam has described about how to layer high order abstract text on top of that. That would work just fine. I'm not going to show you too many examples of concrete terms today. Yeah. This is just standard GHC, yeah. It's a library for GHC. Okay. Has anybody done something like this before? Implemented the Bruijn indices? Yeah. Okay, you two have. Anybody else? You have. It's not the same as you did. Right. Well, it had, but yeah. Right. It's not locally nameless, right? Yeah. Right. So, I mean, it is okay. Okay. So the next thing is sort of like, what is a substitution? I call them substitution environments for no good reason. But what is a substitution? We want to substitute for our variables that are in scope, right? And we can think of a substitution or this environment as a mapping from variables to terms. But how many variables and what scope are the terms that we're going to get from it, right? And so that's why we have two numbers that parameterize our substitution, right? So you can kind of think, so it's a fin m, so it says I'm going to take variables up to m and tell you here's a term for them. And those terms, they can live in scope n. They all have to live in the same scope, but it doesn't have to be the same scope that it came from, right? And now so this is just my type of these environments, and then I need some ways to build them up, right? And I'm going to represent them just as functions, but there's lots of ways you can implement these environments, right? I mean, it could be a vector, like a length index list. It could be an array of size m, where everything in the array has type term n. I'm doing it a function because that's really convenient. It's a very short implementation. Now, what do I need for this, from this type, right? I need to have an empty environment. So this maps no variables, right? And so that's why it takes a variable, a fin, and pattern matches it, but it doesn't need to have any cases. There are nothing of type fin z, right? So that's my empty environment. I need to be able to extend it with another mapping. So this is cons, right? This one up there is like nil, and this is cons, right? So if I have an environment that tells me what to do for m variables, and I have a new thing that I want to add to it, now I have an environment that tells me what to do with m plus 1 variables. And yeah, it all type checks. We also need some other things. Maybe I just want an identity substitution. And here, this is really slick, right? Right? The var constructor of my term data type is an identity substitution, right? it's going to take an environment within variables. It's going to, like, I can use it to replace, if I just replace all my vars with var, I haven't really done anything, right? So I can use this as a way to have a function from fin in to term in, right? And that's the type of var. I can also shift, right? This is a way to, like, increment the numbers, which if you've ever done Bruijn indices, you know you have to do, right? So shifting is an environment that's going to take variables up to m and give me terms in a bigger scope. And that's just like taking all my variables and incrementing all their numbers by 1. Right? And then once I have all of that, I can start to write my substitution function, which I'm calling apply e. How do I apply this environment to a term? Right? And I want you to focus on the type first. Right? So look at the type. Right? The type says I take variables in m to terms in n. And so then I get a term with variables in m. And I produce a term with variables in n. Right? I have changed, by applying that substitution, I found all my variables. Every variable has to have a mapping in this environment. So that m, the first argument to inf, has to match the term. Right? So I have to have a definition for every variable, but I have that identity substitution to make it really easy. If I don't care, I can just use identity. So if I say what to do with all the variables, I'm going to change the scope of my term. And the definition, I know I'm like showing a bunch of code to you really quickly. This is just a fold over my data type. The only interesting cases are the variable case, where I look up in that environment what to do for that variable. So that's line 374. And then whenever I have these binders, I have to modify the substitution to work under the binder. And so I have a helper function called up, right? If I go under one binder, I use it once. And if I go over 2 binders, I use it twice. Right? Otherwise, just go over the term and, right. And then here's the definition of up. It's a pretty standard, just like push things over. You don't want to change the bound variable, so that is just replace variable 0 with variable 0 and move everything over. And once I have substitution or apply e, then I can also talk about composing substitutions. Right, here's another way I can glue things together by doing one substitution and then applying it to the result of doing it. OK, what have we got? Right, so that gives us substitution. This is capture avoiding substitution because I'm doing it all with the Bruijn indices. I don't have to worry about capture. What have we got? Right, we've got this type. Oh, this should be capitalized. We've got this type, and these are the operations that we have on it. Right? Sometimes it looks a little bit like a list, where we can create it using cons and nil. Sometimes it acts a little bit like a function, where we can create it with identity and compose. And it's a monoid in both of those. But sometimes we just need to shift, and sometimes we need to shift multiple times. And then we also, this is where we use it. This is how we destruct it. Right? And so I'm not going to answer this in the talk, but here's a question for you. How would you implement this abstract type efficiently, knowing that these are the operations you have to support? Right? And you want to make sure that you can do all of these quickly. OK, but let's go back to implementing our evaluator. We have substitutions. We're going to use our substitutions for instantiation. Whenever we have a binder and we have something we want to substitute for that binder, we're just going to get the thing that's in the bigger scope, use our substitution with this. So you see here t colon IDE, right? That is creating a substitution that replaces variable 0, the topmost variable, with t, leaves everything else the same, right? And so that's how we can substitute for the binder, for that bound variable. If we have 2 variables, bind 2, then we just put them both in the list, yeah, right, which will substitute for them. right? And it's important that we have this IDE, this identity substitution, because we don't know what scope we're in. We don't know how long this list is. It needs to be an identity substitution for any scope. Right, and that's it. So this instantiate 1 and instantiate 2, this is all we need in order to write our evaluator. Right, so to write our evaluator, right here, here's our application case oh, I showed you a picture that was called by name, but this one's called by value. I'm sorry. Pretend I did call by value before. Here's a call by value variant of our evaluator. We evaluate M, we evaluate N. If M is a lambda, we substitute N's value in the binder. And then we keep evaluating, just like the rule should have said.
Could you show the type of eval like for?
Yeah. It's maybe. We don't. The type system ensures that this case is impossible, but I'm not using a well-typed representation of terms. I'm only using a well-scoped. So I know I can't get a scope error, right? So I know I don't have to worry about evaluating a variable that is out of scope, right? This is an impossible case, but I don't know that I can't get a type error, right? Because the type system is not guaranteeing that for us. Right, and maybe I want to do that, but maybe I don't, depending on what my type system is. Okay. You asked a question. Some of you have asked questions, but I want more questions. This is the end of part 1. Right. So I'm going to ask you to think for a second. Okay, you've seen this stuff. You want to do less next time. What is the library that supports this code? Right? What could you get? What could you get the library to do? And what do you have to do? Like, you invented the language, so you're going to have to write the data type. You're going to have to write the evaluator. But maybe the library could do some stuff. Maybe the library knows what an environment is, right? And has a binder type and can help you implement substitution, right? Even though this, I would say, is a really easy implementation of substitution. And when I say easy, I mean if you mess it up, then you're probably going to get a type error. Maybe. You can still mess it up. Now, when I was preparing this code for MGS, I was making a bunch of examples, and I did mess this up. And what I did is I think I used pair instead of app, right? So it's not a type error. They both take 2 arguments. They're both in the same scope, right? It was a mistake, and I messed up. And I could not find my bug, and I was like trying to find my bug because it's a really subtle bug when you have a substitution error, right? So then, I had started using Claude back in March to try to help. And I'm like, okay, Claude, find my bug. It found it right away. But it would have been better if I hadn't made the bug in the first place.
Yeah. One thing, somewhat minor. Why is it up? Like you said that's because you're under 2 binders. So
Okay, when you're pattern matching a pair, that's the 2 components of the pair. X and Y for the 2 components. Yeah. So the body for pattern matching a pair binds 2 variables. Okay.
And sorry, what would happen if you use 1 up instead of 2, or 3 ups instead of 2?
Okay, let's do 3. You get a type error that says that your indices don't match. Right now. It may take a little while to figure out what the type error is trying to tell you, but at least it's going to point out that you made an error, that you had the wrong number of ups. You're weakening too much. Or if you got 1 out. This is why this is all in VS Code, so it can answer questions like this, which is great. Right? If you don't do it enough, if you forgot, you also get a type error. Right? This is the payoff. Right? Those errors are the payoff. Right? Okay, let's look at what this looks like with the library. Okay, back at the beginning. Okay, let's do it with the library. So we're going to define the syntax and we're going to use the rebound to help us with substitution and alpha equivalence. But we're not going to do quite the same language. We're going to do an even better language, right? Because you notice in the past language, just to make it simple that I could go through in like, I don't know, 15 minutes, I had a pattern matching form for pairs, and a separate pattern matching form for sums, and a pattern matching form for a unit. You don't want to do that. You want to have a pattern that binds the variable in some number of branches. And so that's what we're going to do. So all three of those match forms are going to be all with one match. And then I am going to have a list of branches where each branch is going to have a pattern that binds some variables in some terms. All right, and that's really what we should have done in the first place, right? But let's do that. Okay, so pattern matching, what does that branch list look like? Looks like this, right? We have a pattern. Let's look at the pattern. So a pattern is either a variable, which could be anywhere in the pattern, right? It could be at the top, it could be nested inside, but it binds one variable. Unit binds 0 variables. A pair of patterns, well, if the left binds M1 and the right binds M2, then we get M2 plus M1 variables bound in that pattern. And then if we have an injection, like left or right, this tells us whether it's left or right. If it binds in variables, that's how many variables the pattern binds. So we're using the type to talk about not free variables this time. We're using it to talk about how many variables we're binding. Right, so this is a pattern. I also have this guy here, local name. This is a way that we're going to remember some names that the user wrote down. I have cooked the equivalence class for local name to ignore what that string is. So when I create an equivalence, an eq instance for this data type, those names are not, they'll still be alpha equivalent, even though they might have some different strings buried in there. Right, but I want to, when I print out, I want to print out the same names you typed it in. Okay, so that's a pattern. And then with a list of patterns, it's either empty or we have a binder. So a bind P, that's going to be from our library, and I'll show you what it is in a minute, but it's going to be a binder for M variables in scope N. Right, so we're going to bind some pattern, and then we have some other branches. Now let's look at bind P, and let's look at what these binders is. But I want to point out that we're starting to do some more dependent Haskell here, right? Notice, for example, I couldn't just say deriving show anymore, because there's an existential up there and a GADT here. I could do the standalone deriving for show. I can't do it for eq. And if you were very eagle-eyed, you might have noticed I can do some generic programming here, which I won't be able to do the generic programming for these types, but that's okay. They're smaller and localized. Okay, so we have two kinds of binders. We have our single binders. That was way up here for lambda. We still have a single binder for a lambda. But then we have a pattern binder in pattern matching, right? So both of those are going to come from rebound's pattern binding type, right? And so this bind, right, needs to know what type of variables you're going to be binding, what type of term they're going to be bound in, because you might have a distinction there. Like you might, for example, if you have a language that has values and computations, you might have value variables inside your computations that you want to bind. And so we do need to have two arguments here. Not in examples today, there's always going to be terms for both, right? So we have to know what we're binding in and what we're binding and what we're binding in. And then for single binders, I just want to remember the name for that single binder. For pattern, I want to bind a pattern, right? M variables in that pattern. And then I'm going to be in scope N, right? And then I have a whole bunch of operations about this bind type that the library supplies. I'm not going to tell you how this is implemented. I'm just going to say what it can do. Like you can create a binder You can find out what the pattern is for the binder. You can find out what the body of the binder is in that bigger scope, and you can instantiate it, right? So for single variables, I want to create a binder with this user-supplied name. I want to be able to access that user-supplied name after I've created it. A single binder has a body that has one more, the larger terms in a larger scope. And when I instantiate it, I just need to provide one term to instantiate it. What about for patterns? I'm just giving different types to the same operations, right? So when I bind a pattern, I want to give it a pattern that binds m variables and a body that now has lengthened the scope by m variables, right? I want to be able to access that pattern, get that pattern out. I want to get the body that's in the bigger scope, depending on what that pattern is, and I want to instantiate it, but I need the number of things that the pattern binds m variables. I need to instantiate it with m things, but I already have this data structure that can map m variables to things. That's an environment. Since I'm using environments from the library, I have to say what types of variables those are. That's why we have this term here. But I'm just going to reuse that environment structure that we're using for substitution in this instantiation. Okay. So that's what I have to work with. Let's implement substitution. And I like type classes. So we're going to implement substitution as an instance, using as an instance of some type classes. So here are my two type classes that work together, right? So let's start with the subst type class. This is talking about I'm substituting for variables that stand for terms inside of terms. So that's why I have two parameters there. And that shows up in the type. Let's actually look at the type, the general type of this apply E, right? The general type says that I need an environment that tells me what to do with variables that are going to be replaced with V's, but I'm going to work in some term C and produce a term C. Right. Again, this one we're using term for both, so you can't see the difference. Right. But this is the place where I go and I do that same fold over my syntax. Right. I do the same fold over the syntax, and since environments are now this abstract type, I need an operation to look up. I can't just do an up. Last time, on the previous part, it was a function, so I could just apply the function and say, what am I doing for this variable? Now I have this apply env. That's just from the library to look up. I've called it all recursively. When I get to a binder, the ups are gone, because the binding type knows how many ups it needs to happen. I have an instance of the subst class for my binder type, right? And that's just going to add the right number of ups for me. So I don't even have to look at the error messages, because I just get the type class to figure out how many ups to add. Right? So now it looks even more like a fold. And now you're like, okay, that really is straightforward. Surely you don't have to write all that code. Because look, I could have made that same mistake again. I could have swapped pair and app, right? No, but we have generic programming in Haskell, so we can also use generic programming to generate this, right? And so subst, I either implement apply E, or what's the only special case? The variable case. So generic programming really only needs to know what is the variable in your term, right? So I just have to say in my term that that's the variable case, and everything else is not a variable. right? And so this is pulling out that variable. The REFL is a proof that I'm only pulling it out in the right place, right? That the thing I'm substituting, that this is a variable in the right data structure. But that's it. That's all I have to type. And now I'm done. I still have substitution. The generic programming code, so subst has a definition of apply E that has a default thing that's based on generic programming that only needs this definition of isvar to do the right thing. So I put that in. Then I also get substitution. Yeah?
What's the most general type of isvar?
What is the most general type of isvar?
As in when it's defined.
Yeah, yeah. That one, right? Right.
The equality between B and C,
Yeah.
how is that resolved if you did have like a different,
If you had a,
different syntactic class?
okay, if you were trying to substitute a value variable inside of a computation, and you had a var in the computation type, and you wanted to replace that with a value, that would not type check. Right? And so in fact, I need the proof that that I have the right kind of variable for this environment. And that's what that REFL is doing for me. Right? It's not just there to cut out errors, it's there to actually so I can implement the thing.
Could that be replaced with some way of like embedding B into C? Like if you have like a return or something? I guess they wouldn't come from the same stuff.
Yeah, yeah. Yeah. I mean, var is kind of a return anyway,
Yeah.
but
Yeah, it's just, it would be interesting to
yeah.
see how it works with something with two different categories.
yeah. I don't have that today, but I'm going to be around for today and tomorrow, so we can look at some other examples. And I do have examples where they're not the same in the library example suite. Okay. Okay, so this is what we have to do for substitution. It's not a lot of code, right? What's going on up here, right? We have this subst var thing. That's actually, it's actually a superclass of subst. So I can't create an instance of subst before I say how to construct a variable. And I need this for the identity substitution. Sometimes my code is going to want to create an identity substitution, and it needs the var constructor in order to do that. Just like we saw before, the definition of the identity substitution is a var constructor. And so this is just a way to communicate that to the library, right? So here, like, we have to say how to create a variable and how to find them. Right, and then now I can't use generic programming for branch list. It's got this existential in it. It's okay, it's pretty easy to write. It's the same thing though. I don't have to substitute in patterns because they don't have free variables in patterns, they only bind. The library also supports patterns that have both binding variables and free variables. If you want to have code embedded in your patterns, like type annotations or something like that, see the examples for that. I don't have that today. So I have some examples. What is this? Oh, this is applying our substitute. This is just proving to you that this little bit of code works, right? So let's hope it works. We're going to take a substitution that replaces variable 0 with unit, and here's variable 0. And we should get unit, right? And we do. And this one, here we have a lambda that binds x, but it's got this free variable inside of it because this is 1. Like variable 0 here would just be an identity function. Variable 1 is referring outside the lambda. We should get a lambda that binds x that has unit afterwards, right? And that's what we're getting. Okay. Okay, how does that work though? There is a little bit of magic going on, right? I still have to tell a little bit more to the library about how patterns work, right? So first of all, I have to tell the pattern, I have to tell a little bit to the library about how to find the number of variables that are bound in the pattern. This is a Haskellism, right? Because for terms I didn't have to do this, Because for terms I just said, okay, it's the last argument for the term and it has to be this natural number. That's going to be the number of free variables in the term. For patterns, I wanted to have both patterns that bind variables and have free variables, and so I made it a little bit more general and say, now you tell me which part of that type is the number of binders, right? Instead of just defaulting it always to the last argument, right? And so here I have this associated type. This is just a function. It says, look at this type, pull out the m. That's the number of bound variables. And sometimes you might want to do this at runtime, get an actual number, and so that's where a singleton comes into play. Who knows singletons? That's familiar to you? Good. I'm not going to do a long description of how singletons work. Notice I cannot get this. I cannot implement this code wrong, other than like going into an input loop or something, right? It says you have to give me exactly m back. Okay, this is more about singletons. You really know about singletons? There is one thing about singletons is I have both explicit singletons and implicit singletons. Because sometimes you know from the type what singleton you want, and you can pass it via a type class. And that type class is called snat_i. This is just a type class that holds the singleton nat for I, for n, right? But sometimes you want to pass it explicitly, right? And you can go back and forth, right? If you, we have there's an operation called with snat. So if you have a function that needs an implicit singleton, you can provide one explicitly, and vice versa. Okay, now let's do alpha equivalence. You would think alpha equivalence would be easy, right? Right? It was before. We didn't even talk about it in the first part of the talk, right? Because with the Bruijn indices, it's just equivalence, right? What changed here? Is that pattern matching, right? Right? When I can't derive eq for, I could derive eq way back up here. I could derive eq for the term class, fine. Assuming I have an eq for this list of branches, but I couldn't derive an equality for this list of branches, and I can't derive an equality for this pattern. And I actually don't want to. Right? Why is that? Well, if you think about it, when you have a branch, right, you have this pattern, it binds some number of variables in some body. And I want to compare it to another branch, which binds maybe a different number of variables in some body. And if I'm asking the question, are these the two the same pattern? I don't know how many variables they bind, because that's the existential. And an eq instance is going to be completely useless, because I can only compare things that have the same type. And these two patterns have different types. I don't know what their variables are. Their scope is, how much they do that, that's an existential thing, right? And so what I need is a little bit more flexible version of eq that my pattern type is an instance of, and I use that. And once I compare with that more flexible version, then that's going to tell me not only these patterns equal, but they bind the same number of variables. And then I can start looking at the bodies. So let me put those words into code. Right? So the more flexible version of eq is in the Haskell library. It's called test equality. Right? And it's a member of a type class. Here's the instance for snat, the singleton nat. So if you have two singleton nats and you call the text equality function on them, either they're not equal to each other, you get nothing. But if they are equal, you know that they are the same number. And so you also get a proof that A is equal to B. All right, and that's what we're going to use here, right? Because because you can compare singleton 0 to singleton 0, but you can't compare singleton 0 to singleton 1. They have different types. But you can do test equality. Singleton 0 and singleton 1 are different numbers, and singleton 0 and singleton 0 are the same number. We could, right? But we get a proof that their types are equal to. Right? We're going to do all that with patterns right here, where we make an instance of test equality. Patterns, their index, right? If the patterns are equal to each other, they bind the same number of variables. And so we can return a proof that their number of variables they bind are equal when we compare them for equality. Right? So we make this instance here. This I don't know how to do with generic programming, just because GHC generics falls over as soon as you have existentials around. But it's pretty straightforward. We just go through and compare the different parts. We do have to get these refles and return them. But there's no extra cost for producing this kind of proof, because this is code we were going to write anyway. We're just, as we run this code, we also get this augmented refle, which takes 0 bits to represent. So it's not, there's not really any cost to this. Right, so that, and then once we have test equality, then we can compare branches for equality. So if we have a non-empty branch list where we have this branch B1 and branch B2, we look at their patterns with test equality. That's going to tell us that their patterns are the same and that they bind the same number of variables. Once we know that, then we can compare their bodies to each other. Right? If I had left this part out, and I can do that, say I didn't do this part, I skipped the comparison. Actually, I'll just not pattern match the refle. If I don't have the proof that the number of variables bound is the same, then this call to equals is not going to type check because the types are not the same. Okay, right, and that's how I can get alpha equivalence in this thing. Okay, where's our evaluator? I'm going to flash it at you. I'm not going to show you. It's elsewhere even here. If I go over to scoped eval, here's our evaluator. For pattern matching, we have to go through all the branches, compare them against the patterns, find the ones that matches, build up a substitute, build up this environment when we match the pattern against the value, and then use it for instantiation. I'm not going to go through those details, just so that I have like 5 or 10 minutes to like briefly talk about the last thing. You could ask a question right now to change that course, but let's actually go to the third part. Okay. That's the end of part 2. Part 3. We have we have this data type. We can do great things with it. We can do pattern binding, right? And we have alpha equivalence for it. We have substitution for it. We didn't have to write a lot of code. The library wrote a bunch for us. We could use that to write our evaluator. What else could we do, right? We don't just want to write it, like we're not done when we write the evaluator, right? We need things like a parser, a pretty printer, we want testing infrastructure, right? We could do all that too, right? The scopes don't get in the way. They help a little bit, maybe, I don't know, but they definitely don't get in the way. Okay. Just an overview of what parsing and pretty printing looks like. And the only thing I want to bring up here is that when you parse, you also have to check the scopes, because our data type can only represent well-scoped terms. And so we have to prove, when we create this well-scoped term, we have to prove we can only do it with things that scope check. If we have some terms that have 3 variables, when we parse it and we don't know what binding site that those variables resolve to, then we have to report a scope error at that point. We can't put that into our data structure. And so if you go to the tutorial, it tells you a lot more about how parsing and pretty printing works in the tutorial. But this is the picture, right? You take a string, you parse it. I have a data type just for a name syntax that is not a well-scoped expression form, just for demonstration purposes. You don't have to do it all separate, right? But just for demonstration, we parse to a name syntax, and then I have an example of how you might use that name syntax to do the scope checking, right? How do you make sure wherever you see these names, you keep track of the scope, and then you have to resolve them to indices that are in the current scope. It's not hard, but it's nice that there is an example there that you can look at. And if there isn't something to resolve to, that's when you get your scope error. Going the other way, I have a pretty printer. That's a lot easier. If I have a scope syntax, it's really easy to just turn it into a name syntax. Remember, I have those local names. I remember the names that people told me here. That's the local names there. They're embedded in the scope syntax. They just don't interact with substitution or alpha equivalence. But when we get back here, that's the names that I use, right? Unless they I need to change them for some way, or this is code that people didn't write. I had to make up a name, then I use the made up name, right? But then I have mostly the names that people wrote, and then that's what we use for pretty printing. Okay, here's some demonstrations, right? We parse. Here's my string. I'm going to parse it, and now this parse, right, is actually the composition above, right? I'm not going to show you the name syntax in the middle, right? But it's going to take a string and either have an error or give me my well-scoped term, right? So when I parse it, I know it succeeds. That's why I can pattern match right, and I get the thing. And I can do that with lots of nice examples. And then PP, that's my pretty printer. I can print it back out again so you can see what we got. So, and if I try to parse something that has a scope error, has this free variable, then I detect it, and I can tell you that the scope checking couldn't resolve this variable. So that's closed terms. What about open terms? What if we wanted to parse and print variables that were open? Well, if I know what variables are allowed to be open, I have a version of the parser that I give it a scope of variables, a scope of names, and I look for those, and I say, well, okay, I don't know how to resolve anything, but I know how to resolve y and z, right? And so I can do that, right? So I can parse that, and I get this var2, which is out of scope for this binder, but it's going to have the type that is based on the length of this vector. It's going to tell us what scope I'm getting, right? And so somehow I can communicate that, right? And the same is true with pretty printing. If I have some things that, right, so here, look, G is allowed to have two variables out of scope. When I pretty print it, I need to say what those names are if they don't have local names there, right? And I can pass that in. So we can generalize. We're not limited to only working with closed terms. We can, as long as we have some data structure that says, okay, we are in this extended scope, we can work with terms that work with that scope. Yeah.
So now this starts looking a little bit more like locally nameless.
It is different than locally nameless, right?
Yeah.
Right.
Like
Yeah.
So I guess my point is, like, is it possible to maybe use some of these ideas to repurpose this library so that it can also do locally?
The thing about locally nameless terms is you never have to weaken them. You don't have to keep track of what their scope is. Right. And I had an earlier library, Unbound. I don't know if you remember that, right? Which did locally nameless, but it didn't try to keep track of scopes at all in the type system, right? So you could, like, underneath locally nameless, you have bound variables. You could use this for the bound variables and make sure, and that would replace like local closure and stuff. But I am a little scared of like trying to remember a set of variable names. Like if I wanted to keep track of free variables, and numbers are a lot easier to work with, right, than sets of variables. Maybe, I don't know. Maybe. Okay, last thing. This is just the last thing I want to show you, which is quick check. Again, I'm not going to tell you how this happens, how I wrote this code. I'm just going to tell you the code exists. But I have generators for this well-scoped type, right, which is going to generate well-scoped expressions, right? Not arbitrary expressions, but I mean, we can't represent things that are ill-scoped, so it has to generate well-scoped expressions, right? And it's actually a little bit more expressive than that. For fun, we can choose whether it can also generate well-typed terms. Like the type checker doesn't guarantee that it's well-typed, but I know that it's going to only generate well-typed things. Or I could ignore the types and just generate anything. So I have this constraint. So here this for all is a way to generate things. I could say, do I want scoped things or or do I want things that are scoped and typed? I can also say, maybe I really only want to look at the pure lambda calculus part of my language, or do I want to look at the full language with pattern matching? Okay, so we have some generators. We have an evaluator. We need some properties to test. Let's make sure that that evaluator that I wrote and did not show you very much of is correct, right? Right. So here's a property for the evaluator. Like it's kind of hard to think about properties for evaluators, but here's one, right? What does this one say? Right. This one says that give me a random well-scoped term and evaluate it to a value. And the property is that if I evaluate that value, it doesn't change. Like once I get to evaluate, I'm done. Right. Right. I went all the way, or at least I went all the way. So, and now this is quick check, so I need to get a terminal to run it. Right. And then I need to remember how to run it. Prop eval item potent. And then let's see, what do we want to do? So this is just for let's do first just for the well-scoped things, right? But for the full language, right? And it runs it for 100,000 tests. I'm really thorough, right? And so, right, why did it discard so many? Yeah. I'm evaluating things that aren't well typed, right? And so maybe they don't evaluate because my evaluator returned a maybe, and if there was a type error, I got none from the evaluator. So a type error could cause it not to evaluate, or it could be an infinite loop, and that's why I have this discard after, right? So there were a lot of them. But what if I say, okay, let's only try typed things. But now you see I'm not discarding anything, right? They all pass. Okay, one more test. Maybe we want to know that evaluating is always going to give us something, give us a value. Right, so this is this is checking our type checker, right? Right, you know, this is a way of sort of saying, like, eval exists val, right? This just says that the test passes if I evaluate it and I get a value, and it is a value, right? So if I get nothing, that's going to fail this test instead of discard it, right? So this one, I'm really going to see the difference between typed things, which are still going to pass it, and just scoped things, which should have a type error, right? Right. It's going to fail very quickly. It says, look, if you try to apply unit to unit, we don't get a value. Okay. Now, I have this discard after, but maybe that's not right, because this is simply type lambda calculus, everything terminates, and it terminates pretty fast. So I should be able to get rid of that and say, no, you have to actually succeed in a certain, you have to terminate, right? So here let's do typed for just the pure lambda calculus, right? And this works, right? Things that type check and just the pure lambda calculus.
You need to reload first.
Oh, I gotta reload. You're right. You're right. Okay, it does the same thing. But yes. Okay. But this should not pass, right? But it's just a pure lambda calculus, right? So it's not going to be a type error. Here the counterexamples are going to be infinite loops, or things that take too long to evaluate, right? So I get omega. Anyway, yeah, we can do quick check. Okay, so that's it. That's all I'm going to show you, but I have I'm around if you want to ask questions or you want to look at this more or see other examples or other tests. I have, in the tutorial, I did the tutorial over 4 lectures, so it was much longer than this, so I went into more detail about how scope checking and quick check works. I also did an example of a scope preserving translation. So how does CPS conversion work, right? Which is something that really messes with scopes because it's like introducing new continuation variables every time. But just to demonstrate that even though you're tracking the scopes statically, it's telling you where you need to shift while you're doing that translation to get that translation correct, right? And then I have quick check properties for that translation too. Yeah?
Can this accommodate like typed, like the Bruijn indices or?
So this library doesn't know anything about types, so it can't really help you there.
Okay.
Right. You can, you can't really use it for a typed one because then you would need to know your substitution is not scope preserving, but also type preserving, right? Right. You have more constraints when working on well-typed terms, and this is not trying to help with those kinds of constraints, and it doesn't even know what they are.
Right. But if without the library, if you sort of followed like the idea
Yeah.
of the library.
Yeah.
For a specific thing, do you think
Yeah.
that would be fine?
Can you have a library for well-typed things?
Or not even necessarily like a library, just
Yeah.
like if you were just doing it yourself and just doing
Yeah.
the types of things that
Yeah.
this library does, like do you think you could do that? Or
So there are some libraries in AGDA. Actually, I should have finished with related work, right? So there's some libraries in AGDA that Guillaume Allais and Connor McBride have worked on that are more about how do you do this for well-typed things. I would suggest if you're going to do well-typed things, you go to AGDA instead of Haskell, just because of you can really only accommodate pretty simple type systems in Haskell. You don't have real type level functions. You're kind of limited. I mean, you can, but and it worked okay.
depends how you do it.
Okay, here's my bias. I do a lot of dependent types, right? And that does not work very well in Haskell.
Sure.
Right. And but I have used this library on an implementation of dependent types, so I know that the scoping is enough for even the crazy scoping that happens when you're type checking a dependently typed language, right? And I have so I, in the past, have given lectures at the Oregon Summer School using this implementation of a dependently typed language called Pi4All. That implementation in the past was based on Unbound, my library for locally nameless representation, so that I didn't have to talk about substitution at the summer school and I could really get into how do you type check dependent types. I ported that with Noe's help to this library so that so just to see, port is we had to change a lot, right? Because we're changing how the variable representation is, right? And prove that everything stays well scoped, which the previous library had no idea of scoping, right? So we were able to express all of Pi4All with this library.
Should 178 be unbound?
Yes, I wrote this on the train.
Can you show us your
Yes. Maybe. The, what do you want to see? You want to see?
I think it was in top two subs. What's adding the ups? Oh yeah, what's adding the ups?
Sorry, what is what?
So I think in your substitution, when you're doing like apply, like if you scroll down on like a, yeah, like you're like.
Oh, where are the ups? Oh,
yeah,
oh, the library defines bind, and so it also defines the instance of subst for bind.
Yeah, can we see that? Yeah. Or I think we're talking tomorrow, so we
I will show you tomorrow,
we're
because the
anticipating all these
secret
things.
is that bind, when you have a binder and you substitute into the binder, it doesn't do the substitution yet. The binder stores the substitution. And then, because when you substitute in a binder, you have to do the up and you have to rename, right? And so you can compose those substitutions together. And so it waits until you really need to know what it is. When you open up the binder, you ask for the body of the binder. And then it runs all of the compose, like maybe you've substituted multiple times, right? Composes them all together and then runs them all at once. Right, and so it's a very convenient way to delay the substitution, because that's really what kills you when working with the Bruijn indices, is that you look at something, it looks like it's linear time, but it's not, because every substitution that you have is crawling over the term yet again. Right. But if you can delay the substitutions, and if you do a lot of them, you can compose them together. And sometimes they cancel out from each other. And if you have a implementation of these substitutions that kind of is something you can inspect, and you can notice when you have an identity substitution, you may not have to do the substitution at all.
Is that related to McBrien's code Bruijn?
No. No, for code Bruijn, we're counting the other way, right? I'm not going to be able to explain how she does code Bruijn, and I think like code Bruijn is really good for like a linear type system, for a linear language where you have exactly one use, and so then it doesn't matter whether you're counting at the binder, you're storing. The binders are pointing to the uses, or the uses are pointing to the binders, right? It's the same, right? If you have lots of uses and a small number of binders, then the Bruijn works very well. If you have a lot of binders but a small number of uses, then code Bruijn works well.
Now switching to drag the conversation down into technical. So
Yeah.
if it's not
Yeah.
appropriate, just say so. But on the topic of deferring the substitution, so that like you can gather all the substitutions that will be applied
Yeah,
and
yeah,
not.
yeah,
Okay,
yeah.
but if you're doing this deferring,
Yeah.
and then the substitution is like duplicated as you fold through the syntax tree, can you inadvertently produce more work, even though the act of implying a substitution to a variable is simpler, because there's some sharing about the computation which is not being taken advantage of if you defer it. Do you see what I mean?
I haven't witnessed this in practice. Like if you could come up with like a really pathological example, we could try to witness it.
Right.
But I think you were going to do it anyway, and so deferring it is not going to increase the number of times you were going to do it.
Right.
I did run a lot of benchmarks on this. I think the laziness was more of a factor than anything in these benchmarks, in a good way, because laziness this is actually a really good testament for laziness in Haskell, because when you're implementing things like interpreters and substitution, you want to not substitute for things. If the variable doesn't appear in a term, you want to not actually apply that substitution all the way, right? And laziness in Haskell gets that for free because if you're substituting some thunk for a variable and that variable doesn't appear, you never force that thunk, right? And whereas if you're working in a strict language, then you do want to like keep track of your variable usage more carefully so that you can trim off your substitution and not evaluate things that are not used. And that laziness makes some of the things really fast here, which yay Haskell. Okay, thank you. Thank you all. And thanks for your questions too.